Hello and welcome back to Data Analysis and Visualization. I'm Javita Christie, and this video is in continuation of the previous video where I talked about hypothesis testing. And we saw what a null hypothesis is, we saw what an alternative hypothesis is, and then I explained to you a simulation of a drug trial where people were divided into a test group or experiment group and a control group, and one group was given medicine for flu symptoms. The other group was also given some medicine, but it was just a fake pill that they were given, and they were just told that it's the real medicine. And then we found out in how many days these groups with flu symptoms were able to get cured completely. And then we found the mean differences between those two. We took average of both the groups and found the mean differences. And this video is about now whether or not based on those results. And I also explained to you how you could, combine the control group and the experiment group and find out afterwards if actually the drug trial is working and how to run more simulations of this. So in order to run more simulations, I told you that you could switch over the subject, from one group to another and see how that works out, how the mean difference works out then. So this is where we are going to do exactly that thing. We're going to see the mean difference because we want to find out if the effect that that the medicine is having, whether it is just a random coincidence or is it actually because of the medicine that people are having this sort of a mean difference between the control group and the experiment group. So that's what we are going to find out now. And I'm going to show you some Python code in a Jupyter notebook to calculate something called p-value, which is used in hypothesis testing to check if you should accept the null hypothesis and reject the alternative hypothesis. In our case, the null hypothesis is the fact that the flu medication does not work, it does not do anything, does not reduce the number of days for which the symptoms are there for the people. And our alternative hypothesis is that the flu medication actually works and it does reduce the number of days the people experience flu symptoms. So that's what we are going to see now with a little bit of Python code. So let's proceed to that section. So what you can see here is a portion of my screen, and you can see that there is a group, and at the same time you are given a mean duration. So this is a CSV file which I'm going to attach below the video, so you can also download it and you can run it. You can use it to run your own Python code. So this is a CSV file, and you can see here that this file contains two columns. There are only two things. One is the group and another one is the mean duration. So there is group and mean duration. And then you can see here the group. So there is a group name is either control or experiment. This is control. And next to it, you can see there is mean duration given, which is 7. So that means this particular person belonged to the control group, and the mean duration for that is 7, which means that that person experienced flu symptoms for 7 days. And of course, because the person was in control group, he or she was not given the flu medication, but was given some fake pill to take. And that way we have data here. You can see more data over here. You can see data for experiment group as well. If you can see, notice here, this is just part of my screen, so there is a lot more data available here in this file. You can download it. And this is for the experiment group. So this is a file, and now we are going to run some simulations on it in Python. So this is the Jupyter notebook that I'm running on Google Colab. And you could do the same. It's as simple as just downloading a Jupyter notebook or just going to Google Colab like you would go to Google Drive, and you can run all this code over there. You don't even need to install anything in your computer. You just need a stable internet connection, and all these things will just work out. So I've already written the code here, and I'm not going to write the code. I'm just going to explain the code to you and probably run the code for you. So the first thing we are doing is creating a sample distribution from our control and experimental groups. And I already showed you the CSV file that we are using. So there are 4 libraries that we are going to use. One is the pandas and NumPy, which are used for processing arrays. And I would be in future doing videos on pandas and NumPy, how to use those libraries. But right now for this entire course, I am assuming that you're aware of pandas and NumPy libraries of Python. And this is another library called Seaborn that we're going to be using. And we're going to be using a matplotlib to create a plot. So this is my file, which I'm using, CSV file on GitHub. So I have just attached the link over here, and the link is available down below in the description section of this video. So then we are simply doing pd.read CSV function because we want to create an array that contains the data from this CSV file, which is stored into our df. And then when we do df.head, we can see a couple of things which are present currently in our file. We can see that these are the groups and these are the mean durations. You can see the first 5. And let me run this code for you. So when you want to run the code, you just type the code and press play or run cell, which button which you can see here. And if you do that, it might take a little while depending on your connection, your internet, and based on that, you'll see how exactly it is running. So let's just give it a minute, and yeah, so that's it. It is running successfully and giving me this output, which was already there before also. And now the next code we have here is this code that shows me that the control and the experiment group are available here, and I'm just creating an array of control and experiment, and this can be run. So you can see that that is working as well. Now I want to show the mean values of each. So I want to show the mean of control group. Already the number of days are given for each person going through this trial. But now I want to show the whole average of everybody in the control group and average of everybody in the experiment group. So to do that, this is the code that you need to write. First, you are doing this code when you do dot mean and your writing group is equal to control. That means only those values where the group is control are going to be taken. And from there, the mean will be calculated. So we're finding the average number of days people in the control group are experiencing flu symptoms. And that thing is then stored in the control mean. And for experiment mean, we are doing the same thing, but instead of writing control, we are writing experimental, and we are just doing dot mean. And then what you see here, when I print both the values, you can see it is printing 5.4 and 4.8. Let me run that. So you can see it is printing 5.4 and 4.8. So this means that and this is what I also showed in the previous video, that the control group is having a mean of 5.4, which means on an average, the control group people experienced flu symptoms for 5.4. So these are the people who are given the fake pill, which means they did not have any medication for flu. And on an average, they experienced flu symptoms for 5.4 days. Now, the experimental group experienced flu symptoms for 4.8 days. This was the group that was actually given the medicine, the flu medication. And you can see that there is a difference between this average. There is a control group is 5.4, experimental is 4.8, so the difference between them is about 0.6. And this difference is there. It is there, which means you know that there is something about the medication. Now we need to find out if this difference over here is random, or random in the sense, it could be there, it could be just a random coincidence that there is this difference between control and experimental mean. But we need to find out if it is random or not. So for that, we are going to do the things mentioned here. So I'm going to run 10,000 permutations, and I'm going to randomly shift people from control group to experimental and experimental to control, just to verify whether this 4.8, which is a reduced number of average days, is because of the medication or it's just random. So to do that, of course, I cannot run the experiment again because it doesn't make sense to get people with flu once again and provide them with medications. You cannot run the experiment again, but you can, however, run a simulation. So you can see we are running 10,000 permutations. So what we're going to do is, you can see the mean difference. Mean difference is control mean minus experiment mean, which will come out to be 0.6 or so, which we calculated earlier, control mean and experiment. Okay, and then we have, initially it is 0.6. Then we have data points. So we are getting all the data points from DF. We are getting the mean duration, because this was the file. Let me show you the file again. This was the file. It shows you that this person is in control group. This is the number of days for which this person experienced flu symptoms. So what we are trying to do by this line of code here is get all those data points, get all those values in that second column containing the mean duration. And those are the data points that we're going to work with. And we are creating a list of mean differences, which you can see it's an empty list right now, but later on we'll fill it. And then we have number of iterations. So we are running 10,000 iterations for this. So we are running 10,000 iterations, which means we are going to randomly shift people 10,000 times. And for each time, we are going to calculate the difference between control mean and experiment mean. So this is the loop that's going to run 10,000 times. You can see for I in range number of iterations. So it's going to run from 0 to 9,999. And that's why we are passing number of iterations. We are creating within the loop two empty lists, group 1 and group 2. And now from this is another for loop inside this loop, which is for data point in data points. And here data points are all those data points that we took out here. So for each data point, we are going to perform this. What we are doing is we are doing a random assignment. And you can see I'm using the random function of the np library, which you can see here. There's np.random.randint, and I'm passing 0, 2, which means this is going to take values 0 and 1. 0 would mean false, 1 would mean true. So if this function randomly, I'm passing two integers 0 and 1, and it would randomly return to me either 0 or 1. So if it returns 0, that means it's false. And if it returns 1, then it's true. So it's going to return either one of those things. And here I'm checking, did the random assignment return to me 0 or did it return to me 1? If it returned 1, then I will append the data point to group 1. Group 1 is this list right here we created. So we are going to append this data point to group 1. And if this was, however, false, the random assignment is 0, then we will assign the data point to group 2. So it is a random assignment. We are dividing all the data points into random values and putting them here. And now we are going to calculate the mean difference between group 1 and group 2. So we can do that by doing np.mean, which is a function for numpy, and we can apply that function here for group 2 as well as group 1. So we are just subtracting from group 2, we are subtracting group 1, finding the mean, and whatever is the difference, we are appending it to the mean differences list which we have right here. So you can see we are appending it. And then what we are doing is printing, we're printing the average of those mean differences that we have. And we are also creating a plot using the Seaborn library. We are creating this distance plot of all the mean differences. We are creating a histogram plot, and this is the plot that's created. But let me, however, run this code just to show you that it's working. You could also, if you want to run the code, you could pause the video at this point, take a screenshot or whatever you like, pause and try to type this code out on your own Jupyter notebook and try to run it. Of course, you would require all the libraries, and I'm sure that at this point, if you are doing this data analysis and visualization course, you would be knowing how to install Python libraries and how to use them. So I'm just going to hit run, and we shall wait for this code to run. There are 10,000 iterations. So that's it. It has finished running. This is our result, and what you see here is the mean difference is 0.0008, which is not much actually, which means the average difference between any of the two groups, group 1 and group 2, is actually 0.0008, which means whatever from this itself you can say that the difference which we got, which was 0.6 between the control and experiment group, may not be random, because randomly, if we try to find difference, then the average difference we get is 0.0008. And this is the histogram for the same. You can see the histogram right here. So we need to now find out how many values actually exceed the mean difference of 0.6, which was our original mean difference between the control group and experimental group. So how many of those values exceed? So to do that, we have this data frame here of mean differences which we created. And then we want to calculate how many of these mean differences are greater than or equal to 0.6. And you can see from the graph already that 0.6 would fall somewhere here. And the values which are more than 0.6 are not many, because this is a normal distribution graph, and I've explained what a normal distribution is. So those values do not really fall in this position. They are much further away. So we need to calculate how many exceed this 0.6, and the answer to that is 381. I can run this and show it to you. Okay, this time it is 372. Now the thing is that every time it's going to be different. The reason for that, the last time I ran it, it was 381. Now it is 372. The reason for this difference is because whenever we are running our 10,000 iterations, we are randomly switching those groups. So randomly these values might differ. So right now it is 372. If you run this code, you might get a different value. However, when I'm going to explain this to you, I'm going to stick to 381. It's somewhere close to 380, 370, so we can stick to that. So this is 372 now, right now. Now we're going to calculate p-value, but I'm going to take you through this code a little bit later on. For now, I'm going to go back to the explanation part and explain to you what exactly the p-value is, and then we will come back here to this Jupyter notebook and calculate the p-value. So these are the simulations that we are running, and you can see this was the normal distribution graph that we created, and 0.6 was the actual difference between the control and experimental group right here. So this plot shows the normal distribution of our sample distribution of mean differences. And remember that our original mean difference between the control and experiment group was 0.6. And the mean difference mean, that means when we performed our simulation of 10,000 iterations and calculated mean differences between group 1 and group 2 in our Python code, and created a list of those differences and then took an average of that list, we are getting 0.00087. This could, of course, vary or differ every time you run your code because it is random. However, the point here is not the exact value. The point to note here is that this value is very small. It's so small. So when you are randomizing things, the value is quite small. But when you haven't, if you just compare 0.6 with this really small value, you can see that 0.6 is really much larger. So from this, we get some satisfaction that yes, this difference is not just a random coincidence because we tried to randomize the process and check it. Now, what does mean difference actually mean? What does this mean for us? What does this data tell us? So we see that our real life mean difference of 0.6 lies a bit to the far right in our normal distribution graph. And we see that the mean in our experimental iterations is almost zero. As you know, the mean is almost zero because it's 0.00087, which is almost zero. This means that mean difference between groups is almost purely random and there is no real difference between the groups. So the mean difference is purely random and there's hardly any difference between those two groups. Now, what does that actually show us statistically? How do we show that statistically? What is the probability of the mean difference of 0.6 occurring? Right, whether that 0.6 mean difference is a random coincidence or is it statistically meaningful. So that's what we need to check. So let's check our mean difference values and see how many of these values were greater or equal to 0.6, which we already checked. And the last time I ran the code, it was 372, but before that, when I created this explanation, it was about 381. So I'm just going to show you that. So that's where we calculate the p-value. And we're going to go back to the code and calculate the p-value. But let me just explain first what p-value is. So the probability of exceeding our original mean difference, 0.6, is known as our p-value. What is the probability that we would get a mean difference greater than 0.6? If our p-value is less than a predefined threshold, then we can reject the null hypothesis. So if our p-value, if there's a higher probability of getting a mean difference greater than 0.6, then we must reject our null hypothesis. So when we calculate p-value, we will also decide a threshold value, which we do not want our p-value to exceed. So this means that the difference in means between control and experimental groups was actually statistically significant if the p-value is less than the threshold value which we have decided. In our example of the drug trials, it would mean that our medication works, and the common p-value thresholds that are normally used in trials like these are 5%, or if you want to pull it out of 1, then it would be 0.05. So this is the common threshold of p-value that we have. And in our experiment, when I ran my code previously, it was 381, a number of values which were going beyond 0.6. So that was the thing. Now, if you want to see that, that is the p-value. That was the p-value, 380. That was the number of values going beyond 0.6, 381. And so the p-value, which is the probability of getting values greater than 0.6, would be 381 divided by 10,000, because we ran 10,000 iterations. So out of 10,000 iterations, there were 381 which were going beyond 0.6. So the probability, finding the probability is quite simple. You just divide 381 by 10,000 or 372 by 10,000, and what you get is 0.0381. If you're talking about probability, if you want percentage, it would be 3.81%, which is below the p-value threshold that we set, which means our flu medication does work. And a p-value threshold of 0.5 means that there's a 5% chance that the results can be attributed to random coincidence. The fact that maybe the flu medication is not working and it's just random that these people have experienced flu symptoms for less number of days after taking the medication. And the chance of that happening is just 5%. And this means, because our chance of that happening is 3.81%, which is less than 5, it means our difference in means 5.4 and 4.8 was actually statistically significant. And we've shown through that our results that they support our alternative hypothesis. Our new flu medication does reduce the length of the flu. And you must always remember that p-values are the probability that what you measured is the result of some random fluke. So probability that what you just measured for hypothesis testing is actually a random fluke. That is what a p-value is. And let me just tell you a little bit more about p-value, and then we go back to the Python code and I'll show you how you can calculate p-value. It's very simple, just a one-line code to do it. So saying our p-value is 3.81% means our results have a 3.81% chance of being attributed to a random coincidence. However, 3.81% is small and is lower than the typical 5% threshold used for p-values, and therefore it is statistically significant. So now I'm going to go back to the code and show you very quickly how you can calculate p-value on your own. So let's move back there. So the last time we ran the code, we got this 372 value as number of values which are exceeding 0.6. And now we're going to calculate the p-value. So I'm just going to run this code and show you. P-value is simply calculated by this way. We have the mean difference, which we calculated 372, divide that by the number of iterations, 10,000, and we get 0.0372. So this value might differ if you are running this code on your own, because we did 10,000 random iterations. But the point is that no matter how many random iterations you do, you are not going to get a value that is really high. You won't be ending up with 0.6 somewhere in the middle. So that's what we want to talk about here in this video of p-value. And in my next video, I'm going to continue with hypothesis testing and explain to you a little bit more about how it can be done for linear regression. So I'll see you in the next video, and thank you for watching.